and also act as organizer to, if not possible, to shift my talk early. So I thank you, that guy who is very kind to let me to shift my talk earlier. And so this is my title. The title is a little bit different than the program. It's a fragmentation function and a quark distribution function of pi on the kernel is explicitly SU3 symmetry related. Okay. So this work has been done by collaboration with my former postdoc, Jhongli, in chaos, and also my colleague at NTU. Chung-Yuan now is a PhD student, and Fragmentation is the advisor. So we have published 2 articles, and another third one actually has been accepted. So, the fragmentation function is something similar like a quark. We are more familiar with the quark distribution. But actually, fragmentation function is also very important object in the high energy hadron scattering. Yeah. So, for example, in the E plus E minus, then you have to become they are annihilated into the photon. Then you have the quark pair, and the quark and that quark will become the hadron. So if you have the visualization theorem, you can try to separate the low energy and the high energy physics. Okay. So when a high energy physics, you have the small coupling constant, you can calculate order by order. On the other hand, you have long distance, which means the low energy physics, which is actually essentially not perturbative. You cannot calculate any perturbative QCD. So it remains as something like a parametrization, like a Poisson distribution. So usually in a high energy community, this is just take as an input. You try to extract them from the data. Okay? Then you try to use them in another analysis. And the data suppose should be independent of the process. Yeah. So but because I am a hadronic physicist, so for me this is something I should start. And I try to understand it from although we know we cannot use the QCD directly attack this question. Nevertheless, we hope we can attack this question with some future of the QCD. For example, we know when energy is low, the most important thing about the QCD is the Carnot symmetry breaking. So we try to use some kind of model to study this fragmentation function. That's our motivation. And also so let you see the fragmentation function and the quark distribution. Actually, they are quite near to relate to each other. So they have so-called Drell-Levy-Yan DLY relation. Okay. But if when you try to do a model calculation to apply this relation, you got to be careful because naively field theory perfect, okay, but in the model you always have a lot of concern, so it's got to be careful. Yeah. So now we talk about the so-called elementary fragmentation functions, which means that if you just make some that naively you should sum over all the intermediate state. Okay. However, if you just replace that by just the most simple one, which means you have one quark, you have one quark plus one hadron. Okay. Then quantum number, the flavor, quantum number, color, quantum number, they are still conserved. Okay. So this is so-called one-step fragmentation process. So here you probably have a rather heavy constitute quark. Then you have to emit that heavy quark will emit the one hadron. Okay. So once you have this kind of vertex of quark pseudo-scalar measure. Why is pseudo-scalar measure? Because it's a bit related to the Carnot symmetry. Then you can calculate this elementary fragmentation function. Okay, that's a bit done. So here we will try to our model is so-called a non-local model because this model is somehow related to the incidental. So we all know that classical ambient field theory, you have some certain coefficient try to use the optimization technique, construct an effective action. So then they found something interesting. They can have the quark is moving inside the incident ensemble, and then you can see that it seems that it carries out some momentum-dependent mass. Of course, it's not really quark mass in the QCD. It's some kind of effective kinetic mode behavior. Okay. So this is very important feature of this picture. So we take this picture and make some simple. This is some detail. No time to set. To tell you what kind of model I use. So the most important thing is Lagrange, we can write down Lagrange, but this Lagrange is not complicated. You have this operator there, that's the mass. But that mass is dependent on momentum. Then of course you can couple to the scalar field. So by this Lagrange, we can calculate elementary fragmentation function and quantum distribution. So let me show you this is some certain quantum distribution function. And of course, we are calculating in some model, so you have to do the some QCD equation to the high Q square to compare the data. Here, we evolve to the 27 GeV square. And it looks not bad at all. Okay. The layer one is pi over, this one is KO. The KO, we don't have the data to compare here. Then that one is by the data from the pion, nucleon, and Drell-Levy-Yan. However, if you try to understand the fragmentation function, elementary fragmentation function is not enough because you can see naively you should include the so-called quark J contribution, which means actually there's many steps fragmentation process you can consider. So you can write down this dot as the elementary fragmentation function, and then you can try to do the kind of result. Write down the equation, integral equation like here. Then you just use whenever you have the model of the small d, you plug in, you solve this question. So let me show you the result. So the blue line is the N0 model, which is much easier and much more naive model than ours. So you can see in our model, the small z is from let's say 0.2 to 0.4. The small z part is enhanced, significantly. However, you can see when the fragmentation function from U to K plus, our model is highly suppressed. This is quite big difference between the N0 model and our model. Okay, that's something. And for this elementary function, for example, you go to the pi minus. That definitely identical result if you only consider one step. But here you might have many steps. So the U problem might, after the second step, that might emit the pi minus. Okay. So in our case, the U go to pi minus is also enhanced. So I have a small z. Okay, that's a lot of channels. And now in our model we consider isospin symmetry, and also you can use the charge communication. So you can reduce the independence number of these fragmentation functions. So the upper part is so-called, they are not identical zero in the single state fragmentation process. The later, the downward part is that I call it indirect one, which means their elementary fragmentation functions are all identical zero, but after the result, they are not zero. So it's become quite a complicated multi-channel analysis here. So let me show you the result. Of course, we have to use the QCD evolution to the higher Q square. Here is Q square, 4 GeV. And when compare with the N0 model result, and also compare with the two experiment parameterizations. Experiment installation, then you just use the very simple gamma function type, and then try to feed the data. So one is called HKAS, another one called DSS. They are by the initial of the authors. Yes. And here you can see there is a band. The band is only the HKAS. And you can see the result, you go to the pi plus, this is the most dominant one, and you go to pi 0. Yeah. So our result is in the band of the arrow bar. Okay, and the green one is the NZL. But of course, you can see when you go to a very small z, because in our model we don't have room, so you go to a very small z, that didn't do very well. But nevertheless, in the most region of z is okay. Now, if you go to the most serious problem probably is happening in S go to K minus. So in our model, it's too large in a relatively high z. However, we do have the good behavior in the small z compared to the NZL model. For S go to K minus. This one is probably most unsuccessful channel for us. Yes. And also, if you go to K minus, as you can see, it's highly suppressed in our model. But nevertheless, they are in the shadow of error bar. Now, this one I want to emphasize. This is the most successful channel we had. You can see in this channel, the two parameterization are quite close, from 0.1 to the 1. And our curve is beautifully, almost very well compared to NZL model. And it's highly trivial because this you go to pi minus. This is the result of many multi-channel results. So, well, it might be just accidental. Nevertheless, it's quite a surprise. We don't expect this. And then I can show you the other channel. Yeah, the other channel, well, more or less is similar to the NZL model. Okay, and for this two channel is particularly interesting because you see that our model has a blue line, and our model is somehow agree with the DSS fragmentation very well for these two indirect fragmentation function. Okay, that's more. Again, our results somehow always agree with the DSS quite well until 0.2. Yes. So that's our future plan. Actually, in our model, we just put a pseudo-scalar plan. So naively, we should put more. For example, the one very important thing is eta, because in the SU3, that's eta. Where is eta? Actually, we didn't agree, but that's some issue about the eta, because eta plan have a certain plural component there. Also, we should include the barrier, but the barrier, then you have to consider this like quark in the beta state. So it's not trivial, but surely we can find a way to do it. Also, we should include the vector elements to try to make our result more complete. However, the really goal of this whole project is not just to try to understand its fundamental fragmentation function. We try to work on more complicated and more interesting fragmentation function. For example, like dihydrogen, which will be useful for the destruction of the transversity. So transversity is a kind of odd traced quark distribution. So in many processes, they will couple to the dihydrogen fragmentation function. That project is going very well. And the third one also will try to understand this transverse momentum dependent fragmentation function. That one is much more complicated because then when we have some gauge linker problem, in our model we don't have the gauge field. So this is probably take a more thought. And also the one probably most interesting one is Collins function, but that probably is probably most difficult one. But nevertheless, that's our plan. We want to apply this model to work out, and hopefully to be helpful to the instruction of this, in particular transversity.
Mr. Jin, comments?
Yeah, please.
Okay, let's compare your calculation with the standard definition of a fragmentation function. The standard definition contains a Wilson link. So it means that this function contains not only the final state of the H1,
think very hard try to improve the growth, but that's not easy. For example, the entry-level model, they have a naive calculation for the Fouriers, but later versions, they try to put some growth by hand. That's not very elegant way, but that's the issue indeed, yes. Naively, we could include the growth because our model is kind of institutional model. So then you have to try to make expansion around this classical field and try to get some growth there. Yeah. That's possible. But that's naive. Yeah, we'll try for that. Any more questions?
Is no more question. Since